Let's have the continuation for our lecture video in Geotechnical Engineering under the topic Flow of Water Through Soil. So we have here the continuity equation for simple flow problems. Considering this setup here, this one-dimensional flow problem, that's the reason why it's one-dimensional, because we have here the inflow of water and the outflow of water. So it moves through the soil in a singular direction, and that is downward here. So it's a one-dimensional flow problem. Then let's see the calculations that we can apply in this setup. So here is the figure. So if we are to look for the hydraulic gradient of this entire system, so remember hydraulic gradient I. So for the hydraulic gradient I, so that's right here, for entire system. So this is already here in our study guide, but let's just try to solve them again here. So for the entire system, we have the hydraulic gradient I is equal to the difference in or the total head over the distance traveled by the water. So if we are considering this entire system here, so the total head, that is the difference of the water level here, so the difference of the water level from the inflow to the outflow is H1. So the total head here is H1. Then our denominator is the distance traveled by the water through the soil. So what is the distance traveled of the water through the soil? So this is the soil. We have here the soil 1 and the soil 2. So the water travels from this point downward through soil 1, and that is H1, plus through soil 2 we have H2. So we can put here in the formula, we have here H1 plus H2, and that's for the hydraulic gradient. Now how about the value for the hydraulic conductivity K? Because we have here in this entire system, we have two different soil types, soil 1 and soil 2. Therefore, we are to solve for the K equivalent. So how do we solve for the K equivalent? So again, what kind of formula for K are we going to use? Is it the horizontal or the vertical formula? So the flow of water is from this portion here up to here, and the division of the soil is here. So the flow of water is intersecting the division at a right angle. So if the soil, if the flow of water intersect the soil division, therefore the orientation of the formula that we're going to use is the vertical. Okay. So for the K equivalent, we have here the total H. So the total height of the soil, we have there H1 plus H2, because we're considering the total system, the entire system. Then we have here the K equivalent equals H1 for the soil 1 over the K1 plus H2 for the soil 2 and then K2. So that's for the K equivalent for the entire system. Now for the total flow, for example, we're taking the per meter width. Okay, let's get the small q. And then we have there the Kia, so Kia. But since we are considering the entire system, the K to be used here will be K equivalent, because we have two different soil types. And then we have the hydraulic gradient and the area. Okay? Or should I say small a? Small a if we are considering per meter width. Okay? So that's the calculations to be used if we are considering the entire system. Now how about if we consider it as point to point, okay, or by point? For example, we are to solve for the hydraulic gradient at this point, soil 1, and then at point A. So the location here is Y1 from the top of the soil. So this is the top of the soil. And then we have here up to the point A, we have Y1. So if the question is looking for hydraulic gradient, what is the hydraulic conductivity, then what is the flow, the seepage Q of point A. So first, let's solve for the I, for the hydraulic gradient at point A. Again, hydraulic gradient at point A is the head over the distance traveled by the water. Of course, we will put here the distance traveled by the water through this point down to the point A is Y1. So we put here Y1. How about the head? So if we put here a tube, and then we get the value for the head from the inflow up to the where the water reaches the tube. So if this is the level of water, we get here the value H2. So H2 here will become the head for point A. Okay, so that is for the hydraulic gradient. How about hydraulic conductivity at point A? The answer there is K1. Okay? So we will not solve for the K equivalent because this is only one soil type. Soil 1. How about the flow? The flow of water through the soil in meter width. So we have there QA, small QA, and then we have Kia. But here the K here is K1. Okay? So that's at point A. Now how about if we are solving at point B? Okay, so this is at point A. How about at point B? Okay. So we are considering here at point B. Point B having the location of point B from here up to this point here, point B. Now let's solve for the hydraulic gradient. Okay. So for I, we have here hydraulic gradient I sub B. So the distance traveled by the water through this point up to the point B is equal to, okay, we have here H1 plus Y2. So that is H1 plus Y2. Now, how about the head? Now, if we stick a tube into soil B here, and then we found out that the level of water at this point up to the inflow is H3, then our head here is H sub 3. So that's for the hydraulic gradient. How about the value for the hydraulic conductivity K? What is the hydraulic conductivity at point B? Now, as the water travels through the soil, it encounters two soil types, soil 1 and soil 2. Therefore, we are going to use the K equivalent. We are solving for the K equivalent at point B. Okay. And then, the total width of soil or height of soil that we will use here is H1 plus Y2 equals, we have H1 here, all over K sub 1 plus Y sub 2 and then the K sub 2. So that's for the K equivalent at point B. Okay. Now lastly, how about the flow? So again, flow is Q Kia. So Q sub B is equal to the K equivalent at point B times the I at point B, or the hydraulic gradient at point B, and then the area per meter width. Okay. And interestingly, the flow here for the total system, so for the total system, Q total is equal to the Q of point B and is equal also to Q of point A. Okay? So that's what we call the continuity equation. Okay, so that's how we calculate this. Okay, we solve for the calculations for this setup. So all the formulas are already given here in our study guide. So you just have to copy. Now let's go to the flow nets. Two-dimensional flow of water through soils, and we have here flow nets. Okay. Seepage losses through the ground or through earth dams and levees, and the related flow pattern and rate of energy loss or dissipation of hydrostatic head are frequently estimated by means of a graphical technique called flow net. Okay, so flow net is a graphical representation of a flow field that satisfies Laplace equation and comprises a family of flow lines and equipotential lines. Now here is the criteria that must be met in making the flow net. The first one is that the boundary conditions must be satisfied. Next, flow lines must intersect equipotential lines at right angles. So that is number 2. So in this figure here, given this figure, we, for example, if this is a sheet pile, for example, we have here the equipotential line and the flow line. Okay, so what's the difference of a flow line and equipotential line? So we have here flow line. So it says there, flow line is the path followed by a particle of water as it moves through a saturated soil mass. The path of water. Okay? So in this figure, what is the path of water? For example, we have here the upstream side. So this is upstream side. You can see there the boat. And then this is the downstream side. Okay? So we have there the downstream side. Obviously, the flow of water will be from left to right because the water level here is higher compared to the water level at the right side. So, the tendency of the water is to flow from left to right. And the first one that we will have here is the flow of water on the sheet pile. So, it will move from this point up to here. Okay? So, that's the first flow line. The second flow line here. Okay, so that's the second flow line. This is the third flow line, the fourth flow line, and this is the fifth flow line. And lastly, we also notice the path of water from the upstream to the downstream here at the, for example, if this is the what do you call this? The soil bed, for example, or the rock. So from this portion here to the right. So how many flow line did we have? So we have 1, 2, 3, 4, 5, 6 flow lines. So there is 6 flow lines in the figure. And since we have 6 flow lines, so we have here number of channels, NF. So we're jumping here, so I hope you are following. So if H from the figure is the head, so the difference of the water level, we have here NF, N sub F as the number of flow channels. Number of flow channels, or it is the number of flow lines minus 1. So we have here 1, 2, 3, 4, 5, 6 flow lines. So for the channel, that is 6 minus 1, that is equal to 5 flow channels. So we have here 1, so we have here 1, 2, 3, 4, 5 flow channels. Right, so that's for the flow lines. And it says there that the flow lines, it says here in the second criteria, flow lines must intersect equipotential lines at right angles. So what is equipotential line? So equipotential line is a line connecting points of equal potential energy. Okay, so from the figure, this is the flow line. So for the equipotential line, we have the clue here that the intersection of the flow line and equipotential line is right angle. So our first equipotential line will be from the riverbed because it will intersect the flow line at right angle. So this is the first equipotential line. Next, the second equipotential line. Third, fourth, fifth, sixth, seventh, 8, 9, 10, and lastly, at the downstream side, 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 equipotential line in the figure, and ND, or the number of equipotential or pressure drop, is the number of equipotential lines minus 1. So that is 11 minus 1, we have 10, so it is equal to 10 equipotential drops. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equipotential drops. Okay? Next, we have here criteria number 3. The area between flow lines and equipotential lines must be curvilinear squares. A curvilinear square has the property that an inscribed circle can be drawn to touch each side of the square, and continuous bisection results in the limit in a point. So, if you notice here, the area that is formed by the intersecting flow line and equipotential lines is what we call the curvilinear square. So, we have here a curvilinear square. Okay? So, these are curvilinear squares. Now, this is the reason why this graphical representation is called a flow net, because the resulting diagram here looks like a net. Okay? So, that's flow net. Next, we have the fourth criteria, the quantity of flow through each flow channel. So, where is the flow channel again here? It's at this point, there, okay? So, that is in between flow lines. Okay, so the quantity of flow through each flow channel is constant. Number 5, the head loss between each consecutive equipotential line is constant. Number 6, a flow line cannot intersect another flow line. So as you can see in the figure, the red lines and curves there, it does not intersect another red line or red curve. Next, number 7 criteria, an equipotential line cannot intersect another equipotential line. Okay, so that's the red one, and the flow line here is the blue curve, or the blue line and the curve. Okay, so we have here the formula that we can use in solving for the flow or the seepage. We have there Q is equal to, okay, so small q, because the resulting answer will be in meter length or in feet or in foot per or in foot or per foot. Okay, sorry. So small q is equal to the coefficient of permeability times the head, then that is multiplied with number of flow channels over number of equipotential or pressure drops. Okay. So this formula is for isotropic soil. So what do we mean by isotropic soil? Isotropic soils have the materials, the properties of its material are identical in all directions, or it is homogeneous. So in all direction it is identical. Now how about if it's not identical? So we have here anisotropic soil formula. So we have here small q is equal to the head multiplied with the n sub f over n sub d, square root of the coefficient of permeability at x-axis and coefficient of permeability at z-axis. So one example here. So anisotropic is a property of material wherein it differentiates in its or in one direction it is different, in the other, okay, it is the same. So we can have here an example, for example here. Okay, so we have two layers of aquifers, and this is a solid bedrock here. So we have the first soil layer, soil A. Then we have here soil B. Okay? So these are two different soil materials. Thus, the formula that we will use here is the formula for anisotropic soil. Okay? This is the x-axis and this is the z-axis. Okay, so let's try to solve some sample problems. We have 5 sample problems. Number 13, refer to the figure. So this figure here. Given that H1 is equal to 300 mm, so this is the H1, and H2 is 500 mm. So it's talking about the length of the soil. So let's write here the values for this height of soil. Okay, so what are we going to use here? Mm or meter? What is being asked? Ratio, then mm, then centimeter. Okay, let's just use here meter. Yeah, let's use meter. Okay, so if I put here, this is soil 1, H1 is 0.3. So this is 0.3 meter. And then for soil 2, we have H2 0.5 meter. Okay. And H sub 1, the small h there is 600 mm. So here. So let's write there 600 mm. Okay, or just simply put there 600. Or 0.6. 0.6 meter. Then at Z is equal to so this is an axis. It's just mentioning that downward is Z. And the reference point for this downward is the top of the soil layers. Okay? So it says there at Z is equal to 200 mm and H is 500 mm. Okay? So let's put here the values. .5. At Z is equal to 200 mm, or that is 0.2. Okay, and let's name this as point A. The portion here is point A, right? Just like the setup that we made here a while ago. Letter A. What is the ratio of K sub 1 over K sub 2? B. What is the value of H at Z is equal to 600 mm? So that means from this point here downward 600 or 0.6. So that would be at this point here, because that is 0.3 plus another 0.3. Okay? So for letter B, we will have another tube here later on. Okay? Then let's name that as point B. Then letter C, if K sub 1 is equal to 5 by 10 raised to negative 6 centimeter per second, what is the equivalent K of soils 1 and 2? So let's solve for the ratio first. What is the ratio for K sub 1 and K sub 2? Okay? So what is very useful in this kind of setup is remembering that we can use here the continuity equation. So what is the continuity equation again? The continuity equation is Q total is equal to Q sub 1 and then that is equal to Q sub 2. So that is the continuity equation. Now for point A, at point A here, so at point A, we have Q total is equal to Q sub 1, right? Because in this soil we have here, in soil 1, so the flow is the same. And then remember that Q is Q Kia. So for the total system, the entire system, Q total, we have there Q Kia, but here we have K equivalent, because if we take the entire system, we have two different soil types. So we have K equivalent, the I total, then the area is equal to K sub 1, I sub A, and then the total area. Cancel area because they have the same area. Cancel area. So what is left will be K equivalent. And then for the hydraulic gradient of the total system is we have the difference of the water level here, and that is 0.6. And the total distance traveled by the water through the entire system is 0.3 plus 0.5 is 0.8 equals K sub 1. And then what is the hydraulic gradient of point A? Hydraulic gradient of point A is this. The difference of the inflow level up to this portion here is equal to, so the reference point here is from the outflow. So we have there 0.6 minus 0.5, so we have there 0.1. Okay? So 0.1 over the distance traveled with water up to point A, and that is the Z. So that is 0.2. So this is the distance traveled by the water through the soil from the top up to the point A. So we have 0.2. Okay. So the value for K equivalent now here is equal to 0.667 K sub 1. Okay? So we were able to get a value for K equivalent using the continuity equation. The next formula that we are going to use to eliminate K equivalent is solving for the K equivalent. So if we are solving for the K equivalent, so we now have here for this setup, again, we are going to use the vertical orientation of formula. So we have here 0.8, the total height of the soil, over the K equivalent equals 0.3 for the soil 1 plus 0.5 for the soil 2. Then we have here 0.8 K equivalent. The K equivalent is 0.667 K sub 1. Is equal to 0.3 K sub 1 plus 0.5 K sub 2. So if we multiply this by K sub 1, it will happen. Of course, what's left here will be 0.8 all over 0.667 equals 0.3 plus 0.5 K sub 1. So 0.5 K sub 1 over K sub 2. So that's the ratio already. So we get now the K sub 1 over K sub 2 equals 1.8. So we got the ratio. That's for letter A. Now what's the question for letter B? So what is the value of H at Z is equal to 600 mm? So again, this is the reference point, the top of the soil, and then we have here to find the value of H at Z is equal to 600 mm. And then we will stick a tube in that location. So this is now the tube. Let's draw the tube now. So for example, we have here the tube. Okay, so that's the tube, and then we get the value or the level of water. For example, we just assume where the level of water is. So for example, it's in here. Okay, so the H that it's looking for, remember the H a while ago is located here, and the reference point is from the level of the outflow. So most probably it's looking for H, so this H here. So what is the value of H? Question mark. Okay. So let's solve for that. The value of H here will be if I name this as H, big H, from the inflow, okay, big H. So for letter B, H is equal to 0.6. So this is the 0.6 there. So 0.6 because, look at this. There you go. So this is 0.6, and then this is H, big H plus H. Okay. So that is small h is equal to 0.6 minus the big H. Okay. So at point B, again, continuity equation, let's use that. Q sub 1 is equal to Q sub 2. Q total is equal to Q sub 2. But we will use the Q sub 1 because let's get the some values here. Okay. We will get K sub 1 and this is K from the Q key, K sub 1, I sub A, and then we have the area. Then Q sub 2 here is at point B. If the water is traveling from this portion down to B, it encounters two different soil types. That's why we'll use K equivalent. But this is different from the K equivalent of the total system. So let's name this K equivalent B. K equivalent of B. Then we have there I sub B, then the area. Cancel the area again because it's similar because of the one flow. So K sub 1, I sub A is 0.1 over 0.2, which we got a while ago. And then that is equal to K equivalent sub B. I sub B is the difference of the water level of the tube and the inflow H all over the distance traveled by the soil. So from this reference up to this point here, that is 0.3. Okay, 0.3 plus 0.3, that is 0.6. Therefore, K equivalent B is now equal to 0.3 K sub 1 all over the big H. So how can we eliminate the big H here? Or how can we eliminate K equivalent B? Say, that is using the K equivalent formula. So, the total soil, height of soil from this reference point up to B is 0.6. So we have there 0.6 all over K equivalent B is equal to 0.3 of K sub 1 plus 0.3 of K sub 2. Then we have here 0.6. What is K equivalent B? That is 0.3 K sub 1 over big H. That is equal to 0.3 over K sub 1 plus 0.3 K sub 2. Let's multiply this by K sub 1. So what will happen is we have here 0.6 H all over 0.3. And that is equal to 0.3 plus 0.3 K sub 1 over K sub 2. Now remember, this K sub 1 over K sub 2 is actually the ratio here, which is 1.8. So we have here 0.6 H all over 0.3 equals 0.3 plus 0.3 times 1.8. So H now is equal to 0.42 meter. And what we're looking for is the small h of 0.6 minus 0.42. So H now is equal to 0.18 meter. So that's for letter B. Now what is letter C? If K sub 1 is equal to 5 by 10 raised to negative 6 centimeter per second, what is the equivalent K of soils 1 and 2? So, equivalent K. Where can we find the equivalent K of soils 1 and 2? What equivalent K it's talking about? It's the K equivalent of the entire system. So, if that is the case, the K equivalent of the entire system given here is K sub 1. So what's this? 0.667 times 5 times 10 raised to negative 6. Okay, that is 3 points. So for letter C, for letter C here, we have here the K equivalent is equal to 0.667 K sub 1. So 0.667 times 5 times 10 raised to negative 6. And therefore, K equivalent is now equal to, let's move this. Okay, there we go. So K equivalent is equal to 3.335 times 10 raised to negative 6 of centimeter per second. Okay, so that's for number 13. Okay, so screenshot. Now let's go to number 14. So we have here a confined aquifer underlies an unconfined aquifer as shown. So what does it mean by the word underlie? So to mean underlie means something is a thing is situated under something. Okay. So it is situated under something. A confined aquifer underlies an unconfined aquifer. So it is situated, this confined aquifer here is situated under the unconfined aquifer. So confined aquifer underlies, or I am located under unconfined aquifer. So the figure here given the figure, the confined aquifer is located here, and the unconfined aquifer is this portion here, the upper portion. Unconfined because water can flow through it because of its unconfined state. Okay. So given we have D sub 1 is 59. So let's write here 59. And then D sub 2 is 41. Or let's just write there 41. And then we have H1 as 45. And then H2 is 33 meter. K sub 1 is equal to 35 meter per day. Then we have K sub 2 equals 27 meter per day. And the length is 2 kilometers, or that is 2,000 meters. Calculate the equivalent coefficient of permeability in the horizontal direction. So, horizontal direction, the flow is parallel to the intersection of the soil. So, if it is parallel to the intersection of the soil, then we will use the orientation of the formula horizontal. Okay? So, we have here K equivalent. How about the total length of soil to be considered? The wet dimension of the soil. Again, we considered this in the, I think it was in the second video. We have, or the first video, we have talked about the presence of capillarity. So if the level of the water is located here at the upstream side, because of the presence of pores, the part of the soil at this portion here is being considered as wet also. Okay? So, therefore, we will consider here the total length of soil of layer 1. Okay? So, K equivalent now is equal to 45. Oops. Okay, 45 plus 33 is equal to the K sub 1. Okay, so let's put it in a formula first. So H1 plus H2 equals K sub 1 H1 plus K sub 2 H2. Okay, so K equivalent now. So this is 45 plus 33 equals K sub 1 35 meter per day, H1 45 plus 27 or 27 33. So K equivalent now is equal to 31.615 meter per day. Next, B. Calculate the hydraulic gradient. So the hydraulic gradient is I is equal to difference of the water level from the upstream to the downstream. We have there here. So there you go. And what's the difference here? That is D sub 1 minus D sub 2. What is 59 minus 41? That is 18 meter. Okay? So that is 59 minus 41 all over the distance the water traveled through the soil, and that is located here. So that is horizontally, the distance traveled by the soil is 2,000. So 18 over 2,000. So what is 18 divided by 2,000? That is 0.009. Unitless. C. Calculate the flow of water from one stream to another per meter width. Again, we will use the per meter width, small q, Kia, K equivalent, because we are taking the entire system which consisted two different soil types, the I and the area. Okay, so we have there 31.615 times the A of, or the I of 0.009, then the area. The area will be the area of the wetted part, or the level of the water, the depth of the water. So we have there 59 plus 41 divided by 2, averaging, multiplied with the width. And since we are considering per meter width, we are putting here 1. So small q is now equal to 14.227 cubic meter per day. per meter width. Okay, so that is for number 14. Let's go to number 15. So flow net. The section of a coffer dam is shown. If the coefficient of permeability of the soil is K is equal to 5 times 10 raised to the power of -3 meter per second, determine the seepage into the ditches per meter length of the coffer dam. So this is the coffer dam. Here we have two coffer dams. So what we will going to do here is, since we are solving for Q at this portion here, we are to divide the system into two because it's symmetrical. So the Q that we will solve here will be times 2. Okay? So Q total is equal to 2 times Q. Okay? So let's put here Q total is equal to Q, or 2 times Q. And I will write it also here. Q total equals 2 times Q. Okay. So what is the formula for Q that we will use? We will use the isotropic formula. Q is equal to KH NF over ND. So K here is given. The value of K is given. H, we have here the elevation 38 minus the elevation 18. So H is equal to 38 minus 18. So H is equal to 20 meter. And then looking for the NF, or the number of flow channels. So NF is equal to number of flow lines minus 1. So again, our flow lines is the path of water. So from the figure, we have the first one here, 1, 2, 3, and then don't forget the horizontal part here, 4. Okay. 4. So we have there number of flow channels is equal to flow 4 minus 1, and that is equal to 3. Next is the number of pressure drops, that is equal to the number of equipotential lines minus 1. So the equipotential lines intersect the flow lines at right angle. So this is the first equipotential line. First, second, third, fourth, this is the fifth, sixth, seventh, and eighth. Okay, so there are 8 equipotential lines. So this is now 8 minus 1. Number of pressure drops is equal to 7. Therefore, we can now solve the formula. Q is equal to, what's K again? Meter per second. Okay, so we have there 5 times 10 raised to -3 meter per second multiplied with H, which is 20 meters. Then NF of 3, ND of 7. So Q now is equal to, so 5 times 10 raised to -3 times 20 times 3 over 7. So 0.043 cubic meter per second. So 0.043 cubic meter per second per meter. So per meter because we're using small q. And the total, since it is identical, Q total is 2 times 0.043, and that is equal to 0.086 cubic meter per second per meter. Q total. Okay, so I think that's what is asked here for number 15. Then we have number 16. The section of a sheet pile is shown. So this is a sheet pile wall. The coefficient of permeability of the soil is K is equal to 4.2 times 10 raised to negative 3 meter per second. Determine the seepage Q into the downstream side. So from upstream to downstream, find Q per meter length of the sheet pile. So per meter length, so small q again. So again, we have the formula for Q. So where to put it? Okay, Q is equal to, for isotropic soil, KH, NF over ND. So for this, we have H is equal to 7 minus 2. So H is equal to 5 meters. And then given K and F. So NF is number of flow lines minus 1. So we have here 1, 2, 3, 4, and then finally we have 5. So we have 5 minus 1, and F is equal to 4. Next is number of pressure drops is equal to number of equipotential line minus 1. So we have there 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 equipotential lines minus 1, and D is now equal to 8. So for the formula, we now have here K is 4.2 times 10 raised to negative 3 meter per second times each of 5. Then we have here 4 over 8. So Q now is equal to 0.0105 meter or cubic meter per second per meter. Okay, so it's looking for side per meter. Okay, so this is the final answer. Okay, so that's for number 16. So we have number 17. So this, I think, is the last one. Okay, yes. It is the last sample problem. For the masonry dam shown, so we have, it should be K equals. Okay? So K, or hydraulic conductivity K, is equal to 5 meter per day. Determine the seepage flow per meter width of dam in liter per minute. Okay, so it's asking for liter per minute. B. Determine the uplift pressure at A and B in kilopascal. C, determine the uplift force per meter of dam. Assume that the uplift pressure under the dam varies uniformly. Okay, so let's solve for letter A first. It's looking for the seepage flow per meter width. So it's looking for small q. K, H, N, F over N, D. Again, let's have the values for okay, so there's a certain correction for this drawing, which I believe is the correction also for the book. So if I put here 18, there we go. So this is 1 meter. Okay. Okay, so let's continue. For here we have H now as 18. We have K 5 meter per day. And then NF. Let's solve for the NF. So NF is number of flow lines minus 1. So this is the first flow line, second flow line, third flow line, fourth and fifth flow line. So this is 5 minus 1, so NF is equal to 4. Then we have ND. ND is number of equipotential lines minus 1, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, then lastly 10. So there are 10 equipotential lines minus 1, that is equal to 9. So from the formula, we now have here 5 times 18 times 4 over 9. So Q now here is equal to 40 cubic meter per day per meter, or 40 cubic meter per day per meter, and that is multiplied with 1 over, so 1 day is 24 hours. Then we have here 1 hour is 60 minutes, and then multiplied with 1 liter, 1 cubic meter. So 1 cubic meter is 1,000 liters. So Q is equal to 27.78 liter per minute. So that's for letter A. B, determine the uplift pressure at A. So here at A and at B in kilopascal. Okay, so let's solve that. B. So for first, we need to compute for the pressure head drop. Why is this so essential? The pressure head drop. So this is what we will reduce as the distance progresses from certain points from upstream to downstream. So there is a pressure drop there. So pressure drop is equal to H all over ND. Okay. Now, we have H a while ago as the difference of the water level upstream minus downstream, so 18. And D is 9. So, pressure head drop is 2 meter per drop. Okay? 2 meter per drop. Then next is we solve for the pressure heads. Pressure head at, let's name this as, so what color it is? So it's not quite visible, so let's just use blue. So this is 1, okay. At this portion here we have 1, or that is at A. Point A is at point 1, 2, 3, 4, 5, 6, 7. Point B is 8. And then, lastly, we have 9 here. Okay? So, we need to find the pressure head at H1. Pressure head H1 for point A. So, we have there this dimension from the upstream up to the point 1. So, this is 19 meters up to point 1. So we have 19 minus twice of point 1. Okay. That is equal to 17 meters. Then we have here pressure head HE of point B. That is equal to 19 minus twice of point 8. That is equal to 3 meters. Now finally, we now have the pressure at point A. Pressure head, that is gamma W H1. That is equal to 9.81 times 17. That is equal to 166.77 kilopascal. Next, pressure at point B. So we have there gamma W H8 is equal to 9.81. Then we have here 3 meters. So we have 29.43 kilopascal. That's the pressure at point A and B. Next, C. Determine the uplift force per meter of dam. Assume that the uplift pressure under the dam varies uniformly. So if we redraw here the dam, so we have here the bottom of the dam. Okay. So that's the bottom of the dam, point A and point B. Now what we have solved here is the pressure at point A. We have here the pressure at point B, smaller. Then if we connect them, we have a uniformly varying pressure. So that is uplift force, pressures here. So these are uplift pressures. To solve for the uplift force, we have here. This is the uplift force U. And a while ago, we solved here PA. and then this is pressure B. So U now here is equal to pressure A plus pressure B. Basically, we're just solving for the volume of this. So, divided by 2, multiplied with the bottom is 30 meters. So, 30. Area of a, this one, parallel. So, trapezoidal area. Then, multiply it with the per meter with 1. Okay? This is 166.77 plus 29.43 divided by 2 times 30 times 1. So it's now equal to uplift force is 29, so U is 2943 because it is force, the unit is Newton. Kilonewton, should say kilonewton. So that's for number 17. Okay, so screenshot first. Okay, so that's all for this lecture video for the topic flow of water through soil. Stay tuned for the next topic.